Hello, in today's lecture, we're going to talk about a very simple concept, functions. A function simply maps an element of a set to an element of another set. Let's get started. Okay, so this is Comp 3010, Discrete Mathematics class at Tennessee State University. Last lecture, we talked about sets. Today, we're going to talk about functions. And in the next lecture, we'll introduce sequences and sums, and then we'll talk about matrices, which are basic discrete structures. So what's a function? A function in many problems, actually, we may need to assign a particular element of a set to an element of another set. That's basically what a function is. For example, here we have a list of students in a class and a list of grades. So we may say Adam get A, Rodriguez get A, and so on. We may need to assign an element of a set to an element of another set. As you see here, both Adam and Rodriguez may get A. Okay, but Adam cannot get A and at the same time B. That's the distinction that we are going to have. And functions are sometimes called mappings or transformations. So here is a visualization of a function. If A and B are non-empty sets, this is set A, this is set B, a function f from A to B, a function f from A to B assigns exactly one element of B to each element of A. Okay, so for example, if we have an element of A, it goes exactly to one element of what? B. Okay, and this is the notation that we use. F is from set A to set B. F is a function from set A to set B, and that's how we write it. Okay. Remember, a relation, a binary relation from A to B is a subset of A cross B, right? Similarly, a function from A to B can also be defined as a subset of A cross B. However, there's a restriction in this relationship. For example, if I have A, B is like an element of A cross B, okay? No two binary relationship, okay, have the same first element. For example, A, if A is assigned to B, A cannot be assigned to C. Okay, A needs to be assigned to only one element of what? B. Okay, so I'm just going to skip that. That's a simple notation. Here is the functions. Given the function f from A to B, so we are going to talk about a little bit of some concepts. The set A is called the domain of function f. Set of B, the set B is called the codomain of f. Okay, if the function f takes A to B, B is called the image of A, and A is called the pre-image of B. And the range of f is the set of all images of points under A. Okay, so that's going to be a subset of the codomain. So for all images of A, it maps to a subset of B. That's the range of what? A. And two functions are equal when they have the same domain, the same codomain, and the same mapping. So each element of domain will be mapped exactly to the same element in the codomain. Here is an example. But before that, how do we represent the functions? Let's talk about it first. Either you can have an explicit statement just like this, or assignment, okay? Or you can have a formula like this, or a computer program, and we are going to see examples of that. Here is the first example. And in this one, this is a representation of a function. So my question is, what is the domain? What is the codomain? What's the range? And so on. For example, here, this is the domain. Okay, all possible, the elements of the input set. Function is from here, A to B, which is the domain, and this is the codomain. So this is the domain. Codomain is A, B, C, D, F. Okay, that's the codomain. And the range, even though the codomain is A, B, C, D, and F, you see no assignment is done or no assignment is given to D. And the range is a subset of codomain that consists of only A, B, C, and F. Okay. And pre-image of B, what is the pre-image of B? If we go all the way here, that's the good friend. And what is the pre-image of A? Well, pre-image of A, Adam is mapped to A, Rodriguez is mapped to A. So pre-image of A will be Adam and Rodriguez, the set that consists of two elements, Adams and Rodriguez. How about here? First question, what is FA? This is, by the way, domain. This is the codomain. And the function FA is mapped to what? Is function maps A to Z. So f of A will be Z. The image of D is what? Again, Z, the same thing. The domain of F is the set A. That means the domain is simply A, B, C, and D. That's the domain. And the codomain is simply B, which is what? X, Y, and Z. That's the codomain. The pre-image of Y is what? B, right there. And f of A, that means f of A means range, okay? Range of this function. As you see, even though the codomain is X, Y, Z, the range is only Y and Z, okay? And the pre-image of Z, well, A is mapped to Z, C is mapped to C, D is mapped to Z, so the pre-image will be A, C, D, the set A, C, D. Pretty simple. Here you go. Here's another example. Now we have A as this set, and we have B as this set. Here we have A, B, C, D, and E. Here we have 1, 2, 3, and 4. It says f of A is 2. That means it takes A to 2, B to 1 here, and C to 4 right there, and D to 1 here, and E to 1 as well right there, okay? So now the question is, what is the domain? If this is a function, from A to B, A is what? The domain, B is the codomain, okay? The image of, what is the image of the subset BCD? What is the image? In other words, asking f of set S. Well, if you remember, if you see as a subset of what? A. So basically it's asking what is the image of the subset BCD? Well, B is 1, C is 4, and D is what? 1. So 1 and 4 is what? The image of the subset. What is the range? Range is 1, 2, 4, by the way. What is the pre-image of 4, for example? C. What is the pre-image of 1? The set A, B, and, sorry, 1 is here, B, E, D, and E is the pre-image of what? 1. Okay, here you go. We have a function z, f, from z to z. Well, immediately, this is what? Domain. And this is codomain. Okay, so that's the codomain. And the function is f from z to z, and f of x is x squared. That means it takes an integer x and map it to the square of integer x, okay? So, well, what is the range? What is the range? Even though the codomain is all integers, like codomain is what? Like 1, 2, 3, 4, 0, -1, all the way to negative infinity. That's the codomain, right? But the range consists of what? For example, if x is 0, x squared is 0. 1, if it is 2, 4, 9, 25, and so on. So for example, the square of -1 is 1. The square of 1 is 1. The square of -2 is 4. The square of 2 is 4. Square of -3 and square of 3 are 9. So basically, the range is the subset, which is a subset of what? All integers. So that's called the perfect square, the set of perfect squares. So that's the range. Okay, well, everybody has written a code, I believe, right? As for example, in Java, if you say int sum, let's say that int a, int b. That's a function, right? So basically, sum is a function that maps, that's a mapping from z cross z to z. Basically, it takes two integers as input and returns an integer as output. Okay, so you can also represent functions as computer programs like that. One-to-one function. It's very simple. A function f is said to be one-to-one if and only if f of a is equal to b of f implies that a is equal to b. In other words, no element in the range or no element in the codomain has two mappings from the domain. Okay, for example, here this is one-to-one. Why? For example, here, if I take 1, it has only one mapping. If I have 2, 2 does not have any. 3 has one mapping. 4, 1, 5 has one. Okay, basically, for example, if you have, but this one, for example, if I had, let's say, this guy, instead of going here, if it was going there, you see that, for example, f of 1 is equal to f of, for example, here, f of c is equal to f of d, which is equal to 1. See, they are equal, but c is not equal to d, so that's not one-to-one, okay? In order for a function one-to-one, f of a is equal to f of b implies that a is equal to b. By the way, there's another notation we call injective. If a function is injective, one-to-one, we call it injective. Here is example. In order to show that a function is injective, this is exactly what I described. If f of x is equal to f of y for arbitrary x and y, then it turns out to be that x and y are the same. This is an injective function. However, in order to show that it's not an injective, if you can find one element in the codomain, okay, such that it is mapped, for example, here 2 is mapped, f of a is equal to f of d, which is 2, but a and d are not equal, okay? So you have two elements, a and d, for which f of a and f of d are the same, but a and d are not the same. How about this one? If this function is one-to-one, well, this is a function from integers to integers, right? Well, think about this, f of -2, which is 4, f of 2 is also 4. In other words, if this is the domain and if this is the codomain, this is 4, this is -2, this is 2, both of them are what? Mapping it to the same thing. So in other words, you have f of 2 is equal to f of -2, but 2 is not equal to -2. So therefore, this is not one-to-one. Okay. How about this? Is this one-to-one? Well, think about this. We said that if this is the domain, this is the codomain, assume that I have A and B, okay? Then f of A will be what? A plus 1. And f of B will be what? B plus 1. Assume that f of A is equal to f of B. Okay, assume that they are mapped to the same thing. Then A plus 1 is equal to B plus 1. That means A is equal to B. So the only possible is that A and B are mapped to the same element in the range or codomain, actually. A and B must be equal to each other. So that's one-to-one. Okay. Now we have onto. Well, onto, as the name implies, for every element in the codomain, if we have an element in the domain that maps the element from domain to element in the codomain. This is pretty simple. For example, here, if you get any element from the, for example, one is mapped to, one has an element in the domain that is a mapping from that element to one. Similarly to, similarly to. So this is onto function. For every element in the codomain, we have a corresponding element in the domain, okay? By the way, it's also called surjective. One-to-one is injective, onto is what? Surjective. And here, in order to show that f is surjective, it's very easy. For any element in the B, okay, choose an arbitrary element y in B. Choose an arbitrary element y. Find an element x in A such that f of x is equal to y. However, for example, here, in order to show that a function is not onto, it is sufficient to find one element in B that doesn't have a corresponding element in the domain. Okay, here you go. Find an element B such that there is no corresponding element in the domain that maps that element to this element right there. Okay. The function f of x, x squared, is this an onto function? We say f is equal to from z to z, right? Okay. This is not onto. Why? Because the function takes integers, even negative integers, and maps them to positive integers. Still in this codomain, the negative integers, and we have positive integers, okay, and we have zero and positive integers. You see there are a lot of integers. In fact, for example, here, even the positive integers, for example, 3. Well, square root of 3 is not an integer, for example. So basically, there are numbers in the set, there are integers in the codomain which have no corresponding integers in the domain. So that's why it is not one-to-one. So we said that one-to-one functions are injective, onto functions are surjective. We also call, if a function is both one-to-one and onto, we call it bijective or one-to-one correspondence, okay? So basically, look at this example. This is one-to-one, but not onto. Why is it one-to-one? Because every element in domain is mapped to a different element in the codomain, okay? Not onto. Why? Because this is not covered, okay? Here, this is onto because every element in the codomain have a corresponding element from the domain, but not one to. Why? Because 2 is mapped by A and by D. So, but A and D are not the same. This is one-to-one and onto. Why? See, we covered all the elements in the codomain, so that's onto, and each element from the domain is mapped to a distinct element in the codomain. This is not onto. Why? Because this 4 is not covered, and this is not one-to-one. Why? Because both A and C are mapping to the same element. It looks like there's a delay in the video a little bit. Let's see if it will come. Okay, so there was a delay in the video, so I'm just gonna repeat that. This is not one-to-one. Why? Because A and C are mapped the same element in the codomain. It's not onto because 4 is not covered. And this is not a function at all. Why? Let's wait for this video to show up. Okay, this is not a function. Why? Because as you see, A is mapped to 2 and A is also mapped to 4. That's not possible. Okay, this is okay. A and C. Adams and Rodriguez may have the same grade, but Adam cannot have 2 and cannot have 4 at the same time. Okay, so this is not a function at all. So inverse function. This is a very important concept. So now we have a function, okay? We have a function f from A to B, okay? But this function must be bijective. Bijective. In other words, it must be onto and one-to-one. I'll tell you why, okay? And the inverse function is from B to A, okay? And if, for example, if we have if f takes A and maps it to B right here, okay, then the inverse, f inverse takes B and maps it to A, okay? And this is a function f from A to B, and function f inverse is from B to A. Okay. So it needs to be bijective or bijection or one-to-one and onto bijection. Why? It must be onto. Why? Because from here, let's say it is not. For example, if I have, let's say A, B, C, and then I have 1, 2, 3, 4. And this maps there, this maps there, and this maps here, let's say, okay? So that's good. We define f. This is A, this is B, and f is a function from A to B. No problem, right? So let's wait a little bit about the delay in the video. Okay. So now if I take f inverse is from B to A. Well, if f inverse is B from B to A, it needs to map everything from the B. Now this is the domain of f inverse. And if those two are not mapped, then this is not a function. Okay, 3 and 4 are not mapped. So that means it cannot be a function. Therefore, it must be onto. F must be onto. Okay. Similarly, it needs to be one-to-one. For example, here the inverse takes 1 and map it to A and maps it to C. That's not possible, right? Because the function cannot map an element of domain to two different elements in the codomain. So that means this is also not possible. So it needs to be one-to-one as well. Okay, so it must be one-to-one and onto, otherwise a function may not have an inverse. Okay, here this is a function from A to B. As you see, it is onto because all the elements of B are covered, and it's one-to-one because each element from A is set to a unique element from B. The inverse will take, if F takes D to V, inverse takes V to D, and so on. Okay, is this function invertible? Let's see, we have a set and we have another set. This set has A, B, C, and this has 1, 2, 3. Okay, and A is mapped to 2, B is mapped to 3, and C is mapped to 1. Yes, this is invertible. Why? Because this is onto, 1, 2, 3 are covered, and it's one-to-one. Since this function is a bijection, it has an inverse. An inverse is going to be easy. F inverse 1 will be what? C, because this will be mapped right there. And F inverse 2 will be A, and F inverse 3 will be what? B. Okay, that's pretty easy. How about this one? We have a function f, z to z, so from integers to integers, and f of x is x plus 1. Is this invertible? First, the first question is it onto? Okay, it is onto, obviously, right? Because for any element in the codomain has a corresponding element in the domain. So that's onto. Is it one-to-one? Yes. Because every element in the domain is mapped to a separate element in the codomain. So that's 1, 2. Since this is 1, 2, 1-to-1 and onto, that's invertible. How do you find the inverse? That's the tricky part. So here, okay, this is from Z to Z. This is F, right? So what does it do? It takes X, okay, and maps it to Y. In other words, Y is equal to what? X plus 1. Now the inverse is going to take Y and map it back to X, right? In other words, Y minus 1 will be X, right? So therefore, F minus 1 Y will be Y minus 1. Or you change the variable name to X, that's going to be X minus 1. No problem. Okay, so this is the inverse of what? Function f. Okay. So here you go. That's the inverse. How about this one? Does this have is this function invertible? This is not invertible. This is real numbers to real numbers. Why? Because that is not one-to-one, right? In fact, f negative 1 is 1, f1 is 1. So that's not one-to-one. In fact, it is not onto either, right? Because, for example, um, in the codomain, you have no correspondence for the negative real numbers. So that's not even onto. So that's not invertible, definitely. Okay, so now we'll talk about composition. Okay, composition is important. I'll explain. Well, there's a little bit, but let's see. So you have a function f from b to c. This is set b. This is c. You have a function f from b to c, and you have a function g from a to b. Okay. Then you may have, this is the notation f of g, f of g, f combination or composition of f with g. This is called f of gx, simply. Okay. So what does it do? Well, so here, let me write here, f is from b to c, g is from a to b, then f, composition of f with g will be from a to b. Okay, see here, b to c and a to b, and this is f of g is from a to c. So it maps, this takes an element of set A and maps it to B. And then this takes an element of B and maps to C. Basically, with f of g, takes an element of A, sorry, this is C, obviously, and map it to C. So what does it mean? For example, let's look at this. We have f, okay, from real numbers to real numbers. We have g from real numbers to real numbers. And basically, f of x is equal to 2x plus 3, and g of x is 3x plus 2, and f of gx, which is composition of f with g, is f of g of x. So that means whenever you see x, see, whenever you see x, replace it with g of x. So 2 times 3x plus 2 plus 3. This is what it is. However, by the way, this question mark is basically, it means f of g here. This is here g of f. I guess one of the font sizes, that was not available in Keynote. So that's the reason that I have that question mark there. So f of g is basically f of gx. That means replace this x with the whole gx. And the other one, g of fx, replace this x with the whole f of x. And for example, here, if we have, how about f of g, in other words, f of gx, in other words, f g of x. This is what it is. So you're going to replace this x with g of x. So whenever you see x, replace it with 2x plus 1. That's what it is. However, g of fx, g f of x, in other words, whenever you see this x here, replace it with what? Whole fx, which is x squared. It will be 2 times x squared plus 1. Okay. Graphs of a function. Well, this is trivial. If f is a function from set A to set B, the graph of the function f is the set of ordered pairs A, comma B, A from A, and then B is basically the mapping, the function mappings of A. For example, Think about this function. F of x is equal to x squared, and f is from integers to integers. Then it will be all pairs a, b. That means a is an integer, okay, and b is basically f of a. So for example, if a is 0, b is what? 0 square 0. If a is b, sorry, if a is 1, 1 square is 1. If a is 2, 2 square is 4. If a is 3, 3 square is 9. So these are the ordered pairs, and that's called the graph. Some important functions. We have floor function. For example, if I say floor 3.5, okay, in the real line, this is 3, this is 4, or let's say 3.7. 3.7 is here, right? Floor means the largest integer less than 3.7. The largest integer which is less than 3.7 is what? 3. So the largest integer less than or equal to x. For example, here, if I say floor 4 is 4, because the largest integer, which is less than or equal to 4, is 4. How about 3.999? The floor of this is still what? 3. What is the floor of negative 2.1? Well, this is little maybe tricky. It's not tricky, but let's say that negative 2.1. In the real line, this is negative 3, this is negative 2, negative 1, and this is negative 2.1. What is the largest integer less than or equal to negative 2.1? That's negative 3, as you see here. So this will be what? Negative 3. Similarly, ceiling function. Ceiling function is the smallest integer greater than or equal to x. In other words, for example, 3.7, ceiling will be what? 4. So this is 3, this is 3.7, this is 4. So the smallest integer greater than or equal to 3.7, which is 4. How about negative 2.1? The ceiling, this is negative 3, this is negative 2, this is negative 2.1. The smallest integer greater than negative 2.1 is what? Negative 2. So this will be negative 2. And here is the graph of this floor function. Why? Because if you take, look here, for example, floor of 0 is 0. How about floor of 0.9? That is still 0, right? Anything like 0.9999, this is still what? 0. So that means anything between 0 and 1, excluding 1, is always mapped to what? 0. Okay. Similarly, if you have floor 1 is 1. So 1 is mapped to 1. But anything less than 2 is still mapped to what? 1. Anything less than 3 is mapped to what? 2. Anything less than 4 is mapped to what? This circle here says excluding. For example, here 0 is included and 1 is excluded. Okay. Similarly, for example, here, if you have floor of negative 0, 0, 1, this is negative 1. Anything and floor of negative 1 is also negative 1. So here, I mean, you can observe this is trivial. Okay. And then similarly, this time ceiling function. Ceiling function is very similar. Ceiling of 0 is 0, but ceiling of 0.001 is what? 1. Anything ceiling 999, for example, this is still what? 1. Anything between 0 and 1, excluding 0 and including 1 is mapped to what? 1. Similarly, 2, 3. So this is pretty simple. And factorial function, I mean, everybody's familiar with that. Factorial is basically a function from natural numbers to positive integers, okay? In other words, natural numbers, that includes 0 as well, okay? For example, 0 factorial is 1 by definition. N factorial is a product of all numbers from 1 to n, okay? And Well, this is just simple introduction to what functions. Remember that functions can be one-to-one, can be onto, or can be bijection. In other words, onto and one-to-one together. From domain to codomain, if you have one element in the domain cannot be mapped to two different elements in the codomain. We talked about inverse and composition, and I'll see you in the next video.